All right, I'm trying out this earbud trick to see if it helps with the audio in the recording. So we'll see. Okay, so today we're going to start talking about second order ODEs. And really we're going to concentrate on linear second order ODEs. So that's what we're going to be talking about today. And so linear second order ODEs. Of course, we already know what the ODE part of this means. These are equations that are written in terms of the derivatives of some function, and we're trying to figure out the function. Second order, this just means that the derivatives of our dependent variable that appear are y double prime, the second derivative, y prime, the first derivative, and y itself, we can think of as the zeroth derivative. The linear part means that when we look at the degree of each of the terms, if we think of y and y prime and y double prime as variables, then the highest order that we have is just 1. So there's no, for example, y squared or y double prime cubed or any product of the derivatives. So there's nothing like y double prime times y prime. Only, let's say, degree 1 term. So this is what we mean by linear in this context. So just as in the case of first order ODEs, we have infinitely many solutions in general. And we saw in the case of first order ODEs that these were parameterized by a single constant. For second order ODEs, we will see something different, but very similar. So first example, very simple example, and one I believe that we've seen before. Y double prime minus y equals 0. And so for this ODE, we could probably guess at some solution. So we're going to propose a couple of possible solutions. Y1 equals, or it is y1 of x equals e to the x, and y2 of x equals e to the minus x. And these are really easy to check. We know that y1 double prime is equal to just e to the x. We just take the derivative of e to the x twice. For y2, it's almost as easy. We take the first derivative of this, we get e to the minus x times the derivative of what's up. So that's minus x. And if we take the derivative again, that minus plus. And so we get that in the first case, y1 double prime is equal to y1. So of course their difference is equal to 0. And in this case, y2 double prime is equal to y2. So we have two different solutions here. And now, consider another possible solution. Well, a whole class of solutions. Y of x is equal to C1 times Y1 plus C2 times Y2, where C1 and C2 are constant. So this is really, we're just writing C1 e to the x plus C2 e to the minus x. Right? And we'll see that this is actually this actually gives a solution as well. So if we take y prime of x, well, we just get C1 times the derivative of e to the x, e to the x, and then plus C2 e to the minus x, and then this becomes a minus because of the derivative of what's inside by the chain rule. And if we take another derivative, we get y double prime, and we get c e to the x, c1 e to the x. And now that minus becomes plus again, and we get c2 e to the minus x, which is equal to y. So of course we get y double prime y. And this was true for any choice of C1 and C2. So when we take two solutions, we take two solutions and we form, well, they don't have to be solutions. Let's just say we're taking functions. We take two functions and we form a new function, which is the scaled sum. So I'm writing this, we're taking these two functions, we're scaling them by some constant, and then we're adding them together. So I'm calling this, just for the moment, a scaled sum. We call this some places you will see this called a superposition. Another term that you might see for this is a linear combination. And what we've really done is just we've taken two old functions and we've combined them to create a new function. And in this case, what we've seen is that any superposition or any linear combination of one function and the other function, or one solution and the other solution, gives us a new solution. So this phenomenon of superposition of solutions appears generally when we have I skipped something. I need to introduce a little bit of notation. Let's come back to this. Before I go any further, I want to say, what is the general linear second order ODE? So we've described it, but let's write it out in a formula. So the linear second order ODE, these can be written as y double prime plus p of x y prime plus q of x y equals f of x. So it's just we're just taking these three derivatives, well, the zeroth derivative, the first derivative, and the second derivative, we're multiplying some function by them, and then we're adding these all up. And then we have some term on the right-hand side, which is entirely x. So it's linear because we only have the y double prime, y prime, and y. None of them are multiplied by each other. And then we can kind of think of this in a very similar way to this linear combination that we had here. So in this case, we were thinking of two functions, and they were scaled by some constants and then added together. In this case, we're scaling each of these derivatives, right, by some function p of x, q of x. We could have another function here in front of the y double prime, but just think of it as we divided through by that one. So this one, we can always assume is just one. Okay. And then we're adding them together. So in this case, the thing that we're scaling them by is a constant. We're scaling them by functions of x. And then on the other side, we have this thing that's entirely a function of x that we call f of x. Okay. So this is the general form for a linear second order ODE. And in the case that we had above, so in the case f of x equals 0, we call this, I apologize for my handwriting, we call this homogeneous. Just like in the case of the first order linear ODE. When the right-hand side, which was a function entirely in terms of x, there was no y or derivative of y involved. When this was equal to 0, we called this thing homogeneous. And just like in that case, we have the situation is a little bit simpler, or we can say more about this. So in this case, we call it homogeneous. And any superposition of solutions is also a solution. So this is a nice property of linear ODE. Notice I didn't say second order. Remember, in the case of the first order, we always had a constant out in front. Okay. It was always c times some function of x, right, in the first order homogeneous. We always had this. So we can think of, we had some solution, and then we had linear combinations of that solution. Well, the linear combination, the scaled sums of only one thing. That one. So it's a similar situation. A similar situation. The same thing works in higher order linear ODEs when they're homogeneous, but we won't talk about those right now. We'll come to that later. Okay, so why is this the case in general? Well, let's consider the general first order ODE, which was y double prime plus p of x y prime plus q of x y, and we're assuming this is homogeneous, so this will be equal to 0. And let's assume we have two solutions, y1 and y2. So we'll propose a new solution. Well, we're just gonna form a solution of these two things and see what happens. So we'll let y equal c1 y1 plus c2 y2. So there's their linear combination or superposition. And when we plug this in, what do we get? We get c1 y1 plus c2 y2 double prime plus p of x c1 y1 plus c2 y2 prime q of x c1 y1 plus c2 y2 equals, we're hoping this thing is equal to 0 because that will tell us it's also a solution. So just like we saw before, there's this very useful property of the derivatives. Remember, it splits along sums. So the sum of the derivative of a sum is the sum of derivatives. And we can also move constant multiples outside. So this can be very easily rewritten as C1 Y1 double prime plus C2 Y2 double prime plus P of X times C1 Y1 prime plus P of X C2 Y2 prime. Okay, so that's just this term. Distributing out the P of X and distributing out the derivative. And then finally, this term we get Q of X C1 Y1 plus Q of X C2 Y2. Now what I'm going to do is collect together the Y1 terms. So this is equal to C1 Y1 double prime plus C1 P of X Y1 prime. I've just moved the C1 out in front. So we see all of these are going to be multiplied by C1, finally C1 Q of X Y1. Okay, so that's all the red underline. Now I'll collect together all the Y2s. So that's those three. What I get is C2 Y2 double prime plus C2 P of X Y2 prime plus Q of X. I want to put the C2 out in front for uniformity. C2 Q of X Y2. And I can just group these things together, factor out their respective constants. What do I get? C1 times Y1 double prime P of X Y1 prime Q of X Y1 plus C2 times Y2 double prime plus P of X Y2 prime Q of X Y2. That look more like a parenthesis. Okay, and now we know that because Y1 is a solution, this thing is equal to 0 because it's a solution of that equation. So what we get is C1 times 0 here. Same thing here for Y2. We get plus C2 times 0, 0. And so any choice of C1 and C2 gives us another solution. In other words, any superposition of Y1, Y2 is also a solution. Now this was for linear homogeneous ODEs. Any superposition of the solutions was also a solution. Now, this involved a lot of writing, and we were basically using the same fact twice. We used this ability to sort of distribute the derivative, right? this property of the derivative, which maybe confusingly is referred to as linearity. Right. So we use that twice just in this distribution step right here. Sometimes it's easier to just kind of collect these things together. And a nice way to write that is called operator notation. Operator notation. And so an operator, write this a little better. An operator is really, intuitively speaking, just something that takes in a function and, forgive the evocative language, spits out a function. Right? We had this idea of functions before that they take in a number and then they output a number, right? That was our idea of a function. It takes something in and it outputs something. An operator is something that just works on functions this way. So it'll take in a function and it'll spit out a function. And the archetypical example of an operator is d dx, the first derivative with respect to x. Right? And we apply this thing to a function, this operator. We applied this operator to a function simply by writing it to the left, as if we were multiplying it by the function. So if we wanted the derivative of y with respect to x, we would write it like this, or even moving that y into the numerator, and we just wrote it like it was multiplication. So written like multiplication, if I can remember how to write, remember how to spell. Okay, so so operators are written by multiplication. That's how we designate that we're applying them to something. So the second derivative is just applying the first derivative twice. And so we could write this as something like this. The derivative of a function, and we're just writing things out to the left as if we're doing multiplication. And when we write out this notation, we take this analogy further. Oftentimes we will write as d squared over dx squared f, or even like this. Okay, so this is another operator, and this operator means, well, really the operator is this part right here. And this signifies the second derivative. And we use these properties of these two operators. They have this special property called linearity, which allows us to distribute them across addition. So we can, when we apply, write it like this, the second derivative operator to y1 plus y2. This is just second derivative operator applied to y1 plus the second derivative operator applied to y2. And also we had that we could move the constant up front. So this is a nice property of operators. And we can combine operators, form new ones. And so one example of doing this is, let's combine the second derivative operator And then we'll multiply something by the first derivative operator. And then we'll add to this just a function of x. Okay. So this whole thing together is some new operator. We'll call it L. And what does it mean to apply this operator to a function? Let's say Ly. So we write it like this. We write it just to the left, like we wrote this operator, and writing it just as if we're multiplying by this. We think of this thing as L acting on Y. And so what does this mean? It means that we take this new operator that we've formed by combining the old operators, and we apply it to Y. We get the second derivative of Y with respect to X plus P of X times first derivative of Y with respect to X plus Q of X just times Y. And of course, this is nothing but what we had before for the first order ODE, the left-hand side, but written in terms of operators instead of in terms of these apostrophes. So it's just a little bit of different notation. But what you'll notice is that because this thing had that linearity property, it distributes across addition and scalar multiplication. So does this. And in fact, just multiplication itself, we write these things as if they're as if we're doing multiplication. But here we really do have multiplication of Q of X times Y. And so multiplication, in fact, has this property as well. It's very easy to see that 2 times A plus B is equal to 2A plus 2B. Right. This operation of multiplication is also has its linearity property. So as long as we form this thing by doing multiplication by functions just in terms of x, and we do addition, then we have this linearity property preserved. And so what we get is that L of, let's say, y1 plus y2, this operator applied to the sum of those two functions is equal to Ly1 plus Ly2, simply because of the properties of all of the operators that we use to form it. Second derivative, first derivative, and location. Okay. We also have something like a constant multiplied by a y1. It's just you move that constant out in front by the same kind of reasoning that we would have used for the derivative. And so what we get from this is combining these two things together. L applied to C1 y1 plus C2 y2. Having taken all of these properties and condensed them down into this notation, this is just simply C1 L y1 plus C2 L y2. And applying L just means applying linear second order ODE thing, the thing that makes the left-hand side. And so, of course, because y1 was a solution to, let's write it like this. Our equation becomes this. L applied to y is equal to 0. And we had that y1 was a solution, y2 is a solution. And so over here, we get that C1 times 0 plus C2 times 0, which is just 0. So we can really condense all of this work that we did up here in the old prime, double prime notation, I can get it to scroll. All of this can be condensed down to L of D1 Y1 plus D2 Y2 is equal to D1 L Y1 plus D2 L Y2, which we refer to as linearity, the ability to distribute like that, a property that derivatives and second derivatives, higher order derivatives have. Unfortunately, possibly confusing with the reason that we call these things linear, which is really because all of these things are first degree. So again, have this unfortunate collision of names, two names that mean two different things, but they overlap pretty well in this case. So this gives us, this is just equal to 0. So this is just a notation for condensing things, and we may use this later on. In the course, but it's good to be able to understand it whenever you're exposed to it. Okay, now we're trying to get this thing to scroll to give us some space, and okay. So are there any questions about what we've talked about so far? Okay. So we saw that in our example, and in fact, we saw in any homogeneous case, we got two solutions. Any choice of C1, C2 gave a solution. And so to get a specific solution, we need to determine two constants. So just like in the first order case, we need to determine one constant. In the second order case, we need to determine two constants. And we saw this from the homogeneous case, but this is true in general for second order ODEs. And what I mean this is true in general is that, in other words, we need to determine two constants. In order to get a specific solution, we're going to need to pin down two constants. And this suggests that our initial condition that will allow us to pin down a solution will need to have two independent, and we'll come back to what I mean by independent, two independent pieces of information. Now for when we're talking about second order linear ODEs, these two pieces of information are always two specific pieces of information when we call it an initial value problem. So here's what we have for a second order linear initial value problem. So of course we have our second order linear ODE. That's the general form of that. And then our initial value. So just like before, we had at some value x, 0, we had some y0. But we need an additional piece of information, and the additional piece of information that we always insist upon is what is our solution first derivative. So we get the function's value at a particular point and how that value is changing instantaneously at that point. And that gives us our initial value problem. So those are the two pieces of information we need in our initial value. How did I phrase that up here? Initial condition. Yeah. So this is our ODE here, and this is our initial condition. It consists of two pieces. Two pieces comprise this initial condition. And we have an analogous existence and uniqueness theorem in this case. So we'll suppose P, Q, and F are continuous functions on some interval AB containing our initial condition or our initial point x0 and y0, y prime 0 are arbitrary constants. They're arbitrary real values. So we have an arbitrary initial value and an arbitrary initial first derivative. Then our ODE, the equation that we have, double prime e of x y prime, e of x y, is f of x, has exactly one solution. This is just another way of phrasing what exactly we phrased for our previous existence and uniqueness theorem, which was that the solution exists, so there's at least one, and it's unique, so there's no more than one. In other words, there's exactly one. So it has exactly one solution for which y of x0, exactly one solution, we'll call the solution y, for which y of x0 is equal to y0 and y prime x0 equal to y prime 0. And furthermore, y is defined on all of the interval AB. So wherever our P, Q, and F are continuous, our solution is also there. Also exists, or is well defined. Okay, now let's return to our example. Should I pause for questions? Check and see. How many people are here? See, this is the problem with not requiring attendance. Number of people. I was going to say slowly dwindles, but I should say quickly. A very small number. The dedicated students. So in our previous example, we looked at y double prime minus y is equal to 0, but now let's specify an initial condition. So let's say that y of 0 is equal to 1, and y prime of 0 is equal to 3. So as we saw previously, any y equals c1 y1. Well, we know what y1 is, e to the x, plus c2 e to the minus x. So anything of this form is a solution. So let's try to get our solution from this form, from this superposition, see if it works. So y of 0, we plug that in, we get e to the 0, c1 times e to the 0, plus c2 times e to the 0, and we get c1 plus c2 equal to 1. We take the derivative. This is c1 the x minus c2 e to the minus x. Right? I don't know why I put a 0 there. Y prime of 0 is equal to, plugging in 0, we get c1 minus c2. This is equal to 3. Okay. Now we notice something. Try out the rainbow pencil. I'll see that. So what we end up here at this point in our problem is a linear system of equations, a system of linear equations. We have two equations, and we have two variables. So we have some hope of finding a solution. In general, if we had too few variables, then we wouldn't have a unique solution. If we had, if we had too many variables, we wouldn't have a solution. And if we had too few variables, then in general, we wouldn't have a solution at all. But we have just the right amount of equations and variables. Now, I'm sure you've seen linear equations many times throughout your mathematical career, and so you know that there are a few different ways of finding solutions to these things. So I'll just pick one. What I'll do is I'll take these two equations and add them together. So C1 plus C1 is 2C1. C2 plus negative C2 is equal to 0, and 1 plus 3 is 4. And so what I get is C1 is equal to 2. But going back to this equation right here, I get 2 plus C2 is equal to 1. So of course, C2 is equal to minus 1. And lo and behold, we have our C1 and C2. So we have our solution. We have a solution. Let's say that at this point we have a solution. And that is y of x is equal to 2 e to the x minus e to the minus. But we know that a solution to the initial value problem is unique. Exactly one exists. So we have it. It doesn't matter, once we have this established that the solution exists and is unique, if we can find a solution by any means necessary, by solving it like this, solving a linear system, or maybe it just comes to us in a dream. We just dream it up and it just appears in our heads. We know that that has to be the only solution because we know. So this problem is completely solved. Now, this was nice because we had two solutions. We looked at all possibilities of superpositions of these two solutions in order to find our exact solution, our specific solution. So here's this condition, general situation. Whenever we have a set of solutions and any solution, any possible solution can be written as a superposition of those, then we call this nice. We call this a fundamental set of solutions. So these are the solutions that we need in order to build all of the other solutions. Now, very quickly before I jump into talking about this, we still have 13 minutes. Let me give an example of a case where we don't have a fundamental set of solutions. So before we saw that for y double prime minus y is equal to 0, that we had y1 equal e to the x. This was one possible solution. And I could get another solution just like this. If we plug this back in, we'll see that we get the second derivative of y2 is equal to y2, and so this satisfies the solution as well. However, this set, e to the x to e to the x, is not a fundamental set of solutions. Okay. We cannot get e to the minus x as a superposition of e to the x and 2e to the x. Pardon my handwriting. Okay. It gets bad when I get to the, whoa, what just happened? Okay, there we go. This tablet does all sorts of things that I don't want and rarely does the things that I do want. It's just this program. There used to be a better program, but Windows did an update and got rid of the better program and replaced this upgrade. Okay. Now you're looking at these two things in the set, fundamental set, and you're probably saying to yourself, oh, that's obviously not fundamental set. These two things are basically the same solution, right? Well, it's not so obvious in general. We want to say we would like to say that e to the x, e to the minus x is a fundamental set. But we're not quite there yet. We're close, but we're not quite there. We have to be able to show that whenever we have this this pair of solutions and we form a superposition, we can always form a superposition that will satisfy our initial conditions no matter what they are. As long as it satisfies them, then we know it's unique by our uniqueness theorem, and so that's all we need. We just need to be able to show that we can satisfy that. So that's what we need to be able to show. And in order to do that, we're going to have to take a step back and talk a little bit about linear algebra, or if you took my class in the spring. It was called matrix algebra, sometimes called linear algebra, so it's called matrix algebra. I don't think you did. So if you've taken this class before, this will just be a review of some of the simpler parts of linear algebra. And if you haven't taken this class before, then you will be learning the simpler parts of it. So this is not, it's not hard stuff. Okay, and we're running up against the end of the class, so I want to be careful not to go over, but we will be able to talk about this. So we're just going to confine ourselves for now to the two-dimensional case. In other words, this case that we were talking about before with two equations, two variables. So that's the two-dimensional case. All right, so what do we need to do? Whenever we have two equations and two variables, let's call these variables x and y, just for the sake of simplicity. Okay, we're taking a step back for a moment from calculus, and we're going to be talking about just about systems of linear equations. So we might have a general equation ax plus by equals well, let's write the two. Let's write the two left-hand sides first, because I want to be able to call these things a, b, and c, d. So cx plus dy is equal to something. So we'll call these things m and n. Okay. Now we're doing this in full generality. So we're trying to figure out what values of x and y satisfy the first and the second equation simultaneously. Maybe this is going to be a little bit of work. Well, it's probably not too bad. So we could solve one of these. We could solve for y in terms of x, and we can plug it back into the other one and see what we get. So we could try that, or let's try something else. Let's take these equations and rescale them. So I'm going to take the first one and multiply through by d. So I get dax plus b. I'm going to write them in alphabetical order. Let's write ad x plus b dy equals dm. And for the second one, I'm going to multiply through by b. So I'll get bcx plus b dy is equal to bn. Now I'm in this nice situation where I can subtract one from the other, right? And what I'll get is AD minus BC x, BDY minus BDY will be equal to 0. And finally, DM minus BN. Okay. Now this is nice because now it's just one variable, and we can very simply just divide one side by the other to get x is equal to dm bn over ad minus bc. And should we plug this back in and try to get y? Well, we know that if we plug any value in here for x, then we just take this and subtract it over the other side and then divide by b. So maybe let's try to do that. Let's say y is equal to a m minus ax over b. And so this is m minus a times x. So that's a dm plus a b n, remembering not to mix up minus plus, and that's all over a d minus c. Make this line up a little better. And then all over b. Okay, so I'm going to distribute that division by b. M over b, a d m plus b m over b times a d minus c. And then multiplying through on the numerator, getting common denominators. We scroll. There we go. I will get m times a d minus c minus m times a d plus b. And this is all over b times a d minus c. Hopefully I haven't made any mistakes. My distribution here. But anyway, we get this cancellation here and here. And so we get minus mbc minus mab b ad c. And what we get in the end is minus m. All right. So why that happened? Oh my God. What is going on? Okay. I cannot tell you how glad I'm going to be not be teaching a class over Zoom. Okay. Finish yourself. Finish the rest of it yourself later. That's a word problem. Anyway, we can solve for this, but what we end up with at the end is this AD minus BC in the denominator for Y and AD minus BC in the denominator for X. So in both cases, we have, let's celebrate being done, changing colors again. Let's use this other rainbow pen. Okay, let's see what this looks like. So we have a solution as long as, this is ridiculous, as long as AD minus BC, it's also lagging, right? AD minus BC is equal to 0. Greeners. Okay. So we have AD minus BC is 0. And that's from our original problem right here, A, B, C, D. Okay. What we found is that we can always solve this as long as our AD plus BC, is not equal to 0. That's very important. We have no solution when AD minus BC equal to 0. Okay, so we can't find a solution in that case, and we can find a solution that's not equal to 0. Now this system of equations, AX plus BY is equal to M, and CX plus DY is N. This can be written in a very compact way, and this is where the matrix part of matrix algebra comes in. So we simply represent this as A, B, C, D in this square block like this. And then vertically, we write our variables, X, Y. And we think of this as a kind of multiplication called matrix multiplication. The notes go into much more detail about this, but I'm only giving you the most important facts right now. So these two collections of symbols are ways of writing the same thing. We're just writing the exact same information, but in two different ways. Now, that's how matrix notation started out. So an example of matrix notation. This is how it started out, was having a convenient way to collect together all of the information about a big system of linear equations. Turned out that this was a very useful thing to study in its own right. And so we have this quantity associated with this matrix right here. So we call this thing the determinant. Determinant. And the reason is because it determines completely whether or not we have a solution. A, B, C, D. So in the 2x2 matrix case, my handwriting is getting progressively worse. Yeah. The determinant is just equal to AD minus BC. And we want this thing to be not equal to 0. So next time we'll come back to this concept of the determinant of a matrix. We're going to form the matrix that we need to find the determinant of, that will tell us whether or not this fundamental set will always be able to find this C1 and C2 no matter what. So computing that determinant will out. Okay. So we'll stop there for today, and I'll stick around if there are any questions, but otherwise I'll see you.